Hello, good morning. Now we'll see how to find the Fourier transform of periodic signals. Myself, Dr. Shaila Dinkarapte. Uh, Here we will be making use of the Dirac delta function. We have already seen how to find the Fourier transform of a periodic signals. Now we want to see if the signal is periodic. Can we just generate establish some relation between Fourier transform and the Fourier series? Because for Fourier series, we calculate the Fourier series for periodic signals and we calculate Fourier transform for the periodic signals. Now, for the periodic signals, can we establish some relation between Fourier transform and the Fourier series? That is the particular aim in this particular lecture. Now, what is the condition for the Fourier transform to exist? We know that in case the Fourier transform, if we want to consider the condition that should be satisfied for the signals in order that we can calculate the Fourier transform, is that the signals must satisfy Dirichlet conditions. That means the function must be integrable. In the sense it must be the energy must be finite. It is required to extend the theory of Fourier transform to all such periodic signals or power signals as well. So what we desire to do is we desire to combine Fourier series and Fourier transform and treat Fourier series as a special case of Fourier transform. Both these conditions can be fulfilled if we make use of the Dirac delta function or the unit impulse function. Now let us see how we can do it. Consider Dirac delta function. What is Dirac delta function? Delta t, it is defined as delta t is equal to 0 for t not equal to 0 and integration minus infinity to infinity delta t dt is equal to 1. So it exists and it is having very small width but amplitude such that the amplitude multiplied by the width, the integration turns out to be 1. So how to find the Fourier transform of delta t? Fourier transform we can calculate using directly the formula. Integration minus infinity to infinity delta t exponentiation of minus j2 pi ft dt. So when we integrate this delta t is existing only for t is equal to 0. So if we put t equal to 0 in this, exponential term will become 1 and hence the corresponding Fourier transform is 1. Means Fourier transform will be a constant value for all frequencies. That means if the signal is concentrated in time domain, it will be spread out in the frequency domain. And if the corresponding function is concentrated in the frequency domain, it will spread out in the time domain. That is what is Heisenberg uncertainty principle. Now let us see how to find the Fourier transform of the DC signal. DC means the constant value, constant amplitude signal in time domain. There is no frequency attached to it. Frequency is 0. So what we do is we assume that DC signal, so constant amplitude signal, can be viewed as a double-sided exponential signal. On either side it will be exponential function, but the corresponding exponentiation term a will be tending to 0. So we assume that it is equal to e raised to at where a tends to 0. Okay. So how we find the Fourier transform? Fourier transform, we just write down the formula. Limit as a tends to 0 because we are assuming that this is a double-sided exponential signal with the limit that a tends to 0. So with this assumption, we write this as limit a tends to 0, integration minus infinity to infinity, e raised to minus a mod t because we are considering the values of time extending from minus infinity to infinity, e raised to minus j omega t dt. This is the formula for Fourier transform. Now just change the, split the limits from minus infinity to 0 in one term and 0 to infinity in the other term. So when it is minus infinity to 0, we'll have e raised to a minus j omega t dt because in that case a will be positive, t is negative. And when t is positive, you will have minus into bracket a plus j omega t dt. Now we integrate. So when you integrate this term, you will have e raised to a minus j omega t divided by a minus j omega integration minus infinity to 0. So similarly, this positive term. Now we take limit as a tends to 0 for this term. When you take integration, this term will be equal to 1. When you integrate, this term will also be equal to 1, but with a negative sign. So this term will become positive. So 1 upon a minus j omega plus 1 upon a plus j omega. When I take a tending to 0, you just simplify this and you get a single term as 2a upon a square plus omega square. When a tends to 0, this will be equal to 0 provided omega is not equal to 0, isn't it? Because if omega is equal to 0, it will be 0 upon 0 and it will be undefined. It will go undefined. So for all omegas not equal to 0, it is equal to 0. And what happens at omega equal to 0? For omega equal to 0, x omega, j omega is a into delta omega, where we find this value of a, capital A. Then what will be the amplitude? It will be concentrated in the frequency domain. But what is the amplitude? Amplitude will be given by minus integration minus infinity to infinity 2a upon a square plus j omega d omega. So we integrate this term and we find how much will be the value at omega equal to 0. So it is equal to 2a upon integration minus infinity to infinity 1 upon a square plus omega square d omega. So you integrate this, put the limits, and you find that x of j omega becomes 2 pi into delta omega. 2 pi into delta omega. So this becomes pi by 2 plus pi by 2. So it becomes 2 pi. So x of delta omega is 2 pi delta omega. That means whenever the signal is well spread out in time domain, that is a DC signal, what will happen in the frequency domain? It will be a single line at frequency omega equal to 0, because delta omega will exist only for omega equal to 0. What is the amplitude? It is 2 pi. So it is well concentrated in frequency domain now. Now let us see how we can make use of Dirac delta function and use frequency shifting property of Fourier transform to find the Fourier transform of sine function. Now consider the exponential signal. Exponential signal as e raised to j2 pi f0t, where f0 is some frequency. Now it is a spectral line at amplitude 2 pi at omega c. Now let us see how we calculate it. X of t will transform to x of f. So what will be exponentialization of j2 pi f0t into xt? It will transform to x of f minus f0. This is what is the frequency shifting property of Fourier transform. Okay. Now consider xt as a Dirac delta function. So x j omega is 2 pi delta omega, and if you evaluate it at omega equal to omega minus omega c, you get 2 pi delta omega minus omega c. Now how you get this? 1, if xt is equal to 1, it is a Dirac delta function at t equal to 0. So it transforms to 2 pi delta omega. This we know. When xt is equal to 1, it transforms to 2 pi delta omega. So if I multiply this 1 by exponentiation of j2 pi f0t, what it will transform to? It will transform to 2 pi delta omega minus omega c. That means it will be a spectral line at omega c of amplitude 2 pi. So this is the corresponding Fourier transform of exponential signal. Now consider a sine wave. Sine wave can be written as 1 upon 2j exponentiation of 2 pi fct minus exponentiation of minus j2 pi fct. So pi upon j, it will transform to pi upon j. So this 2 will be getting cancelled, and I will have just pi upon j delta omega minus omega c minus delta omega plus omega c. So it will be one spectral line at fc, one another spectral line at minus mc, minus fc of amplitude equal to pi. This they will just change the phase. So Fourier transform of periodic CT signals like sine and cosine function. See, when we consider sine function and cosine function, they are well spread out in time domain because sine function exists between minus t is equal to minus infinity to t is equal to plus infinity. Now, the result is useful for finding the spectrum of the carrier wave in the communication signal. So when we consider communication systems, we have one carrier and there is one modulating signal. And when we generate the modulated signal, we want to see how the corresponding spectrum would look like. What will be the corresponding spectrum for the carrier signal? It will be one spectral line at fc and another spectral line at minus fc. Now, if you modulate it, you will have fc plus fm, fc minus fm, the spectral lines at fc plus fm and fc minus fm. So we can study such spectra if we understand this particular Fourier transform of the sine wave using a Dirac delta function. Now, Fourier transform of periodicity signals. Now, if we want to find out the Fourier transform of the periodic signal, what I do? Now, the periodic signal, how the periodic signal is? The periodic signal is xpt is equal to m is equal to minus infinity to infinity x of t minus m t 0. So this is existing at t equal to 0 and it is also existing at t0, 2t0, 3t0 and so on. So I am writing a generating function. Generating function means I am writing a function for one period of that periodic signal. I can write it as xpt between minus t0 by 2 to t0 by 2 and is equal to 0 elsewhere. So I am concentrating only on minus t0 by 2 to plus t0 by 2. That is one complete period of this particular periodic signal. How periodic signal looks like? It is this periodic signal. But how it is between minus t0 by 2 to plus t0 by 2, it is equal to xpt, it is same as xpt, but otherwise it is 0. So we are concentrating only on one period of the periodic signal. Now, if we consider this generating function, we can write down the Fourier transform because it is aperiodic. So I can write the corresponding coefficients as Cn, Fourier series coefficients, as 1 upon t0, integration minus infinity to infinity x of t, exponentiation of minus j 2 pi n t upon t0 dt. This is according to the Fourier transform formula. So I can write it as 1 upon t0 into x of n upon t0, where x of n upon t0 is the Fourier transform of xt evaluated at n upon t0. So if you evaluate it at n equal to 0, you get the corresponding coefficient for xt. When you evaluate it at n equal to 1, 2, 3, etc., and if we calculate all these coefficients, you will get the Fourier transform of xpt. So xpt, I can write it as summation m varying from minus infinity to infinity x of t minus mt0 equal to 1 upon t0 summation x of n upon t0, where this n varies from minus infinity to infinity. Sorry, this has to be n. Exponentiation of j 2 pi n t upon t0. So I am in a position to write the Fourier transform of the periodic signal by concentrating on only a single period of it and writing down the Fourier transform and then extending this to the corresponding periodic signal, that is the repetitive signal. So consider the aperiodic pulse train and Fourier transform. So consider the ideal sampler in the sense we have a periodic pulse train. So this is delta t. So when I sample the signals at sampling period of t0, what I do, I take first sample at t equal to 0, then t0, 2t0, 3t0 and so on, and also at minus t0, minus 2t0 and so on. So this is what? This is a periodic train of delta functions. Now, how to find out the Fourier transform of this periodic train? What I do is I concentrate only on one period of it, that is at t equal to 0. So I write delta t as delta m equal to minus infinity to infinity delta t minus mt 0. So what will be delta tt summation this, and what it will transform to? It will transform to 1 upon t0, m bearing from minus infinity to infinity delta t delta f minus n upon t0. So there will be one particular delta function at n equal to 0, then 1 upon t0, 2 upon 30, 3 upon t0, and so on. So a delta function in time domain is giving rise to delta function in the frequency domain. Consider now inverse Fourier transform. Let us say that the Fourier transform is given by 1 upon j omega square plus 5 j omega plus 6. Now what I do, I simply do partial fraction expansion. So this denominator will be decomposed into two terms, j omega plus 3, j omega minus 2, j omega plus 2. So 1 upon j omega plus 2 minus 1 upon j omega plus 3. If I calculate the corresponding k1 and k2, k1 is 1, k2 is equal to minus 1. So how to calculate xt? Xt will be equal to e raised to minus 2t minus e raised to minus 3t into ut, because we know that 1 upon j omega plus 1 transforms to e raised to minus t ut. So I can directly calculate the inverse Fourier transform. So find inverse Fourier transform of, suppose I am given the x j omega is 2 cos omega for omega less than or equal to pi and equal to 0 otherwise. How I write this cos 2 pi? I can write cos 2 pi as e raised to j omega plus e raised to minus j omega by 2, and that 2 will cancel here, so it is just e raised to j omega plus e raised to minus j omega into e raised to j omega d omega. This is according to the formula of inverse Fourier transform. So I can just integrate this, and you will find that the integration is 1 upon pi 1 upon t plus 1 sine pi t plus 1 plus 1 upon t minus 1 sine of pi t minus 1. So this is the corresponding inverse Fourier transform. Because this particular e raised to j pi t plus 1 e raised to minus j pi t plus 1, this will become a sine function, and this will also correspondingly be a sine function. Now consider inverse Fourier transform of this particular xj omega. Again, I just have to decompose it into two terms, decompose the denominator into two factors first, and then find the coefficients k1 and k2. After I get the values of k1 and k2, when I put the values of k1 and k2, I get this as the corresponding expression for x of j omega. Now what I do, I write down inverse Fourier transform for this term, it will be e raised to minus t, and for this term it will be e raised to minus 3t ut. So I can directly get the inverse Fourier transform because I know this particular formula. Thank you. Now consider inverse Fourier transform of this particular function. It contains three terms. So I will have to evaluate this k1, k2, k3, and then form this particular function, and then directly evaluate the inverse Fourier transform. So it is just on same lines. So I may not repeat. Thank you.